So, very good afternoon to one and all. Myself is Gautham Gopan, and I'm a student of SRM University, India. So, I'll be here presenting the topic integration of sensor fusion for enhancing GPS navigation. So, with that, let's start. This will be the basic stature flow we'll be following throughout the presentation. This is just for your notice. Coming on to the first part, the abstract. So the pivotal aim of this entire research paper is to analyze and demonstrate the various innovative methodologies of incorporating sensor fusion with the existing GPS navigation system. As you all know, we are all frequent flyers in our day-to-day lives, and all the commercial aircrafts uses sensor systems that are individually dependent on each other. And there are possibilities of extreme failures due to other natural calamities as well as other circumstances. So sensor fusion is such a topic that will help us eliminate all these things from the aircraft industry. And in this research paper, we'll be mainly focusing on how this can be implemented into military-based aircraft because as you all know, unlike commercial aircrafts, military-based aircraft travel at much more higher velocity and they are in turn evolved with higher orientations. So with that thought in mind, let's move ahead with the problem statement. So why do we need the need of infusing sensor fusion into the existing system? So one of the biggest reason that is facing in our aviation industry right now is that there are high discrepancies in the data flow that the system receives or the pilot is showcased with. And all these issues are caused with either the faulty hardware or in circumstances where the hardware completely becomes irreusable due to the natural causes. So these are conditions where the system as a whole or a pilot as a whole failures and human life and property can be at risk. So that is why we need to integrate such innovative technologies in the existing hardware. So coming to what is actually sensor fusion. So basically sensor fusion is the technique of combining two or more sensors and combining the data that you receive from two or more sensors are basically resulting in a much more reliable and convenient data to the system. So the main aim of sensor fusion is to overcome all the limitations that are caused by the damage and bad running of all hardwares out there. And the main reason why sensor fusion is going to be a huge hit in almost all industries is that the sensor fusion enables the system to have a much more better understanding about its environment around it. Moreover, the integration of sensor fusion is highly cost efficient and very simple to be added to any existing hardware because of its high flexibility. Moving on, what are the advantages of using sensor fusion? And one of the main advantages of using sensor fusion is that it increases the overall quality of the data that the system is fed with. Now, I can explain to you this with a simple example of an accelerometer. Imagine you're using an accelerometer to calculate the acceleration. And as you all know, no matter how good a hardware is, there are always possibilities of inductions coming in between. So most probably no known sensor will give you a correct reading of 9.8 meter per second. But on the other hand, we can counter this issue by using multiple number of accelerometers and combining and taking the average of all those values and thereby giving it a final data. And this, in fact, helps in reducing the noise factor by the square root of the number of sensors. Now that is one method. And the other method is by infusing sensors of different kinds. Like on another example, imagine that you are going on a trekking and you need to find at which point you are facing towards. And obviously you'll be using a magnetometer. But again, a magnetometer inside a mobile phone will be having to face interferences with the metal objects that are already present in the mobile phone. And that is where a system like a gyroscope, which can be infused with the magnetometer, and thereby the noises of both the sensors cancels each other out. The gyro will be able to understand if the movement or the change in data is actually caused by any metal interferences or is actually caused by the movement of your phone. So again, coming to the next most important advantage is that it can increase the reliability of the data. Now, I can explain to you this by I'm sure most of you have seen pitot tubes. They are just pointing tubes that are pointing out of the front of a commercial aircraft. Now, these tubes are mainly used to determine the airspeed of the aircraft. And especially, I mean, and maybe not in our part of the world, but especially in parts like Canada, the Icelandic region, or the northern regions, there are extreme cases of cold and snowstorms where all these pitot tubes can fail at a single point, even though the aircraft is using three different tubes. There are possibilities of all three being failed. So at these moments, we need a system that calculates the speed without actually taking any external readings. And that's basically what sensor fusion does. You can estimate the airspeed by using GPS and atmospheric wind models, and especially with all our supercomputers and exponential knowledge about how weather changes, we are in a position to predict the airspeed at a very accurate level and almost accurately enough that it can challenge the data that is created by the pitted tubes themselves. Coming to the third most important advantage, it can estimate unmeasured state. Now, I can explain you this by considering a DSLR camera. A DSLR camera can take a picture of an image of an object that is, you say, 2 kilometers far away. But the same 2 kilometer far away object will have the same pixel values of any object kept close. So basically, using a single DSLR camera, you're not able to find out the distance between the camera and the object. But on the same hand, if you are able to develop another camera, put it side by side, infuse the images together, and thereby creating a three-dimensional image, we'll be able to find the relative distance between the two objects. And this is being heavily used in the photographic and cinematographic industry, especially with the introduction of 360-degree cameras, especially the ones you see in the GoPros. Moving on, the fourth important part is that sensor fusion can increase the overall coverage. Now, most of our vehicles nowadays have reverse parking sensors. So even though individual sensors send individual data, a single sensor is only able to cover about 40 degree of angle. So basically, you can't get an efficient system by just using one sensor. You need to use multiple sensors, thereby creating a whole cocoon around the car. And thereby, whenever an individual system is needed, its data is given more priorities. So basically, from all these four different advantages, one thing that we have to understand over here is sensor fusion is a topic that has been highly underrated in the past, and it has the unique capability and the beautiful capability of involving in our lives every day without ourselves even knowing about it. So it's high time that we gave sensor fusion the priority that it actually deserves. Now, how sensor fusion can help with GPS navigation? The most important part is linear acceleration. Linear acceleration is essential for GPS navigation system because it is what helps the whole entity to determine the possible locations of how the object is tracked. The time lag is mostly dependent on linear acceleration. Now let's see how sensor fusion can help with determining linear acceleration. So there are basically two different ways. One is by again predicting the linear acceleration and removing it from the measure before using it. Now, how are we able to do that? This can be simply done by sending all the data that a pilot sends to the engine of the aircraft, running it through a simulation, and there are n number of algorithms out there which are completely efficient in doing that. And by doing this, without even actually giving the commands to the engine, we can predict at what speed or at what linear accelerate will the aircraft be actually traveling in. So by running all the simulation, you are able to develop the value of linear acceleration before we actually even do the movement. But one of the biggest disadvantages of this system is that this can only be done if you are using a vehicle that is traveling at a speed less than, you say, 300 kilometers per hour. And this is not applicable, especially in cases of military aircraft, which are in need of doing high maneuverability at 600 kilometers per hour. They might have to do 90-degree turns. So this system completely fails over there. Now, that is where another solution comes into place. We basically try to create a threshold value. A threshold value means we neglect anything that's under a particular value. In this case, we consider 1G as a threshold value. Anything that is not under that category is completely neglected. By doing this, we are doing a favor to the system by only providing it with the necessary data that it actually will need in the future. And completely, we are completely avoiding it by giving any rubbish informations. So how this can be further improved is by adding a gyro. Gyro is essential in the system because while we are doing all these prediction stuff, we actually stop the system from actually determining the attitude or the orientation of the aircraft. That is especially where the gyro comes into place. The gyro will act as an angular rate measurement unit and which help us to create a delta angle which can be again predetermined and corrected in the existing readings. And this whole process is called data reckoning. Moving on, the second most important use of sensor fusion in GPS is to determine the attitude of the aircraft. Now, again, we can do this by using two different ways, either using an accelerometer and a magnetometer or by using a gyro itself. And both have their disadvantages and advantages. The advantages of the first case is that they produce absolute measurements, whereas in the case of gyro, they produce measurements that are a bit more relative in nature. The disadvantage again of accelerometer magnetometer is that again, since they are physical mechanisms, there are possibilities of disruptions. And in the case of gyro, it needs constant recalibration every time the aircraft goes through a certain hours of flight. We'll have to bring it back to the shed, reincorporate it, reincarnate it. So basically, it's a cost-effective process. But how can we focus on all these disadvantages and advantages and counter all of them? And now this can be done by using a Kalman filter. A Kalman filter is an algorithm that is mostly popular in the sensor fusion industry. Kalman filter has a unique capability of converting the advantages of the accelerometer and countering it with the disadvantages of the gyro, and countering the disadvantages of gyro with the advantages of the accelerometer and gyro. Basically, the Kalman filter is so flexible that you can even determine at what rate the readings are taken. Like for example, you can reduce the rate of reading of the accelerometer to 10 hertz per second, or even increase it to almost 300 hertz per second. Basically, you are given the complete authority of what quality of data that is fed into the system. So moving on, how fusion of GPS with IMU for navigation can be a game changer in the military industry. Now again, IMU is an initial measurement unit, and it basically is a comprehension of accelerometer, magnetometer, and a gyro. And basically, it has the capability of finding the orientation of the aircraft, which is completely unnecessary for a military-based aircraft. Now, adding this to a GPS sensor will provide us with a unique capability of enhancing the whole GPS navigation system as we know it. Because by doing this, we are at the same time, without any time lag, we are able to find the orientation, position, and the velocity of the system. So basically, now focusing more on the military-based aircraft, as you can see in these images, they are intended to do high velocity changes in their directions, and so basically they need data to be fed to them at a much more higher rate, and basically at hundreds of times per second. So basically, we are trying to create a system that rather than going in when investing much more heavy money on creating a hardware that will do much better than the ones used in a commercial aircraft, we are trying to use the same technologies or the same hardwares that we are using in the commercial aircraft and upgrading it with the latest software segments in order to get the optimal output from these existing hardwares. That is the main aim of this whole research paper. Moving on, I'll be trying to explain you what some of the simulations that we were talking of all the details that I explained through the previous slide. And all these images that you can see over here was derived from MATLAB's post-dissemination algorithm. Basically, it's an algorithm that gives you the unique capability of running various different kinds of activities. Basically, you have the authority to determine the angular rate of change, the velocity, and even the natural conditions of what an aircraft might have to face in real life. So all these are simulations of what actually happens in the real world. Now, if you please notice over here, the red box is actually what shows the actual ground truth. That is exactly what the aircraft goes through. On the other hand, the blue box is the one that the system is trying to find out, or the system is trying to predict. So this is the basic prediction happening over here. Now let us go more into the simulation itself. Now the first simulation that we are doing over here is for objects traveling at a medium velocity, or basically basically we are talking about commercial aircraft. Now in order to show the importance of how sensor fusion can enhance GPS navigation, for this initial simulation, we are turning off all the IMU sensors and only running the GPS sensors. And as you can see, the orientation estimate is completely off. The red box is focusing in another direction, and the estimated orientation is completely off the hooks. And if you can see the position meters, yes, position is actually somewhat accurate. But coming into the quantity and distances, you can see errors of plus and minus 2 meters. And yes, plus and minus 2 meters for a normal human being might not be a huge value, but when it comes to aviation, it's a huge value. So now let's see how the simulation acts when we increase the velocity, or when we comes into terms of military-based aircraft. Now, basically what we're trying to do over here is by making small changes into the existing algorithm, we can make the simulation run the same set of operations for an entity that's traveling at much more higher velocity. For example, say 800 meters per second. So basically, And here also we are only using the GPS sensors to show how GPS sensor alone is very incapable of giving us proper data. So as you can see, the ground estimate is way off from in relation to the estimated orientation, and you can see there are high discrepancies in the position, or you can see all these curves in the graphs, all these noises, and coming into the contrarian values, they are completely off. They are completely off means they are off by more than 5 to 6 meters, which in cases of military aircraft can lead to complete catastrophic accidents. So basically, we don't want all these to happen in the real life. And that is why we think that sensor fusion can help all these. Now let us see on how the simulation gets affected when we include the IMU and the GPS and we run both of the sensors at the same time. As you can see, once you add the IMU into the mix and sensor fusion takes over, you can see the ground estimate and the actual truth is actually a lot similar. I mean, there are very minute changes. Even the position is so accurate. And coming to the contrarian distances, as you can see, the error is now coming down to as low as zero point 0.5 meters, which again, I do agree, it's not a completely efficient system, but a completely efficient system is highly hard to reach. But yes, we will keep our promises on that. But still, for time being, this is a much more improved results than what we saw when only the GPS was used. Now, concluding on all these, we can see that the GPS alone is going to create a data flow that is highly incapable and extremely irreliant, and can also lead to huge accidents even in the commercial sector, but and it can also lead to catastrophic disasters in the military sector as well. Whereas on the other hand, if we are able to incorporate sensor fusion, we will be able to do a lot of costs cutting, as well as we'll able to create a continuous and smooth and reliable data flow to the systems of a military base aircraft. As you can see, these are the two comparisons of the readings when only the GPS was used and when a system that included GPS and the IMU was used. Now, coming to the conclusion of the entire presentation, these are the points that we like to emphasize on. The importance of software. Software is something that is highly taken back in the industry as a whole, because we as a human society have been heavily investing our time and our efforts on hardwares. I mean, whenever a hardware proves incapable of doing a job, rather than trying to twitch it and trying to make it much more efficient, we in turn go and find a replica of it or a replacement for it. We go and shell out tons of money in order to buy a much more better hardware. But that habit has to stop. We have to give more importance to software. And softwares like the Kalman filter and sensor fusion can enable us to get more out of the existing hardware components. So that is the basic importance of software. Coming to the efficiency, yes, sensor fusion is a highly efficient system, because since we are using multiple number of sensors, there is no way that we are able to create a data that is bad or incapable. Sensor fusion is highly efficient since we are using multiple sets of sources for our inputs, and thereby our outputs will always be reliable. Coming to the affordability and cost effectiveness, I mean, it is a common fact to the public that anything related to the software is much more cheaper than when we are thinking about anything that's related to the hardware industry. Because mainly all these algorithms are already existing, and all these algorithms are extremely useful. They can be just added to any of the existing systems. Now, accessibility and quality. Yes, there are like how we saw in the previous example, there are cases where there are still errors in the reading, and I do agree with that. But this is just a base research. I mean, we are going to progress more further into this. But coming to the accessibility, yes, all these softwares are already existing in the market and they are there for our use. Coming to the reliability, yes, again, since we are using much more number of sensors and there are always backups present to help us if any of our system goes down, this sensor fusion is highly reliable and scalable. Coming to the flexibility, yes, one of the main advantages of Kalman filter is that by adding small changes to the entire main code of the algorithm, you can make it adjusted to any of the existing hardware. The only thing you need to do is switch a bit over there, change a few of the values. That's it. You're ready to go. Basically, it's much more simpler than going out and getting a new hardware and implementing it in the whole and making a whole system uneven, or basically creating the whole destroying the whole rhythm of the entire system. Now, coming to the conclusion, me and my team through this research is just trying to showcase the world that It is high time that we stop spending enormous amount of money and effort on improving the existing hardware. Rather, I think it is time that we give more importance to the software behind it. And I strongly believe that a good software will be able to give out the 100% efficiency of any hardware. And I hope that this presentation will be a landmark and a further references for the coming generation. So with that, I conclude. Thank you so much. I'm open to any questions. If you have any, please do ask. I'll be more than happy to answer. Thank you, sir.